Hello again, everyone. I'm going to apologize for these notes being kind of out of order in that um, it's just it's going to take me a little while to get everything organized and in a more logical order. So I just ask that you bear with me and I'll try to fill in any gaps as we go along. All right, this video, essentially, we're going to talk about what are called mole ratios. Now, mole ratios is a very important aspect of this class in that it's going to help us do something called stoichiometry. Stoichiometry is extremely important to us in that it's going to allow us to calculate a lot of things about a given chemical reaction. However, there's a difference between a ratio and a conversion. Now, conversion, we've talked about that before. It allows us to change units but not the value. So the key here is a mole conversion allows us to change our units, okay, such as grams to liters, etc., etc. A ratio actually is important to us because it allows us to change compounds. This is especially important because when we perform a chemical reaction, we're going to mix together different things to produce a product or products, things that we want. So we have to be able to figure out how much of a given compound do we add to this, of this, in order to get the amount that we want out of it. Kind of like a recipe on a cake or a dinner. You know, you have to have the right ratio of ingredients, otherwise things don't turn out the way you want it to. That is the essence of what we are talking about here. All right, so the first thing we need is a balanced chemical reaction. We cannot have, so a mole ratio without having this first taken care of. All right, so must. So we must have a balanced equation. That is vital to all of this. Now, below I have kind of an example here, all right, where we're mixing aluminum with oxygen to get aluminum oxide. All right, going through this, we look again for balancing purposes. I like to go side to side. We've got one aluminum here, we've got two aluminums here. That's fairly easy to fix. I can put a 2 here, but I'm not going to yet because that's not my biggest problem. My biggest problem lies here with the oxygens. I got 2 and I've got 3. All right, so let's take care of that first. Remember, when we have a situation like this, we're going to look for the lowest common multiple. Well, the lowest common multiple of 2 and 3 is 6. So 2 times 3 is 6, and 3 times 2 is 6. But the 2, remember, the coefficients multiply everything. So these 2 aluminum now become 4. So now we go 4. So 4, 3, 2 for the balanced chemical equation in this particular case. All right. I have to make a point here in that we are looking for what I call, unique mole ratios. A ratio can be written in one of two ways. As you've seen in mole conversions, we can write it as 1 mole equals 22.4 liters or 22.4 liters equals 1 mole. However, even though we've reversed it, it's still the same ratio. All right, so we are going to look for unique comparisons. In this case, the easiest way to do it is very similar to math. You're going to FOIL. Now, what I mean by that is we're going to take our 4 aluminum, so 4Al is to, well, let's take it to our first right here, which is oxygen, 3O2. That's one unique ratio. If I reversed it, okay, so put the oxygen first, it's still a comparison of aluminum to oxygen. It does not change what we're comparing. Okay, that is what it means by unique. All right, now, aluminum, however, can also be compared to this. So we can have 4 aluminum, 4Al, and we can compare that to the 2 aluminum oxide. You will notice I am including the substances, not just the numbers. If you just put the numbers, it means absolutely nothing to us. You must also include the substances this time. That is vital. All right, now I've compared all those. However, I'm not done, because I can also then move over to oxygen. The oxygen can be compared here as well. So that means I can take 3O2, whoops, sorry, meant to put the dots here, 3O2 to 2Al2O3, or to the aluminum oxide. You'll notice I did not simplify here. You can if you want. However, every time you manipulate a number, you run the risk of making a mistake. And sometimes it's a very simple, easy mistake. But it can cost you if you're not paying attention to your details. Besides, it's also easy to go back and double check. Did I pull the correct numbers from in front of the substances that I wanted? All right? Okay, same thing here. Let's take a look at another example. Here, I've got, let's see if I can get that down there. Oh, whoa. Sorry guys, I don't know what just happened there. Alright, let's see if I can, I do apologize guys, I'm not exactly sure what just happened there. Alright. So let's see if I can get this down. Alright, so we're going to look at this. Now, as I said before, when you've got oxygen, or any element that is part of both products or even part of both reactants, you want to save that for balancing last. So in this case, I'm going to start off with carbon. I've got 3, and I've got 1. Remember, 3 to 1 ratio, or 1 to something ratio is always nice. So we end up with, so we'll multiply that by 3. That gives me 3 carbons and a total of 6 oxygens. Because remember, that multiplies everything. Now let's back up here and go to the hydrogens. I've got 8. I've only got 2 over here. So 2 goes into 8 4 times. So now I've got 8 hydrogen. But 4 times 1, because remember, no subscript is a 1. 4 times 1 is 4. That means I've got 6 plus 4 oxygens for a total of 10. All right, I've got 2. So I'm going to put 5. Again, under normal circumstances, we do not include the 1s, but for our purposes, we're going to have to, simply because of computer issues, things like this. All right. Now, the addition of 1 extra compound in the mix means we went from 3 unique mole ratios to a total of 6. All right, we're going to do the same thing we did last time. We'll start off with the propane. So 1C3H8 is to, and we'll go right here next door, 5O2. Okay? That's 1 ratio. Then again, we can go to the next one in line. 1C3H8 2, 3 CO2. Again, we're not done, and we can also compare it to this. So we get 1 C3H8 to 4 H2O, 4 water. Then, just like before, we're going to repeat the process. We're going to move one over. We're going to start with O2. 5O2 is to 3 CO2. Then this can also go over here. So we got 5O2. Oops. Sorry, there we go. 5O2 to 4H2O. And then, of course, finally, we can also compare the carbon dioxide to the water. So our last one, our sixth one, is going to be 3 CO2 to 4 H2O. Again, taking the time, going step by step like this, foiling, in essence, like with mathematics, I know you guys love that, is probably your best way to do this. All right, for the mole ratios, why mole ratios? Okay, first of all, it allows to change compounds. Okay, when we do something called stoichiometry, we're going to have to go from one compound to another. This is the only way to do it. All right? The other thing it allows us to, or is going to allow us to do, is to calculate out what we call theoretical yield. All right. In other words, if I mix so much of one compound with so much of another, how much of a given product will I get, or how much do I need to get what I want? All right. That will be a later video. Okay. Now, at this time, I would like you to try this. Okay. I'd like you to try this one. All right, so please pause the video here and then give it a try. Let's see if I can do that. All right, so if you tried that, these should be your answers. Once again, you'll notice I do have an opportunity here, like 6 to 2 could become 3 to 1, and 6 to 3 could become 2 to 1. Or, sorry, yeah, 3 to 1, 2 to 1. So you can simplify if you wish. Again, I prefer taking the numbers as is because it's easier to check. Anyway, I hope this helps. Good luck. And if you have any questions, as always, you may feel free to remind me. Okay? Have a great day.